Computer systems is a computer programming class. And when I say computer programming, what I mean is writing C programs. Computer programming is writing C programs. Now, why do I say that? I say that because C is sort of the baseline programming language for the operating system that we're dealing with in this class, or the operating system family, and that is Linux or even historical Unix style systems. The way you write programs that can interact with the operating system, that can do the sort of thing that we're interested in this class, is you write them in C. So we're going to be writing a lot of C code, but there's actually a sense in which we could say that a lot of the other programming that you do is less of programming and more like scripting. The reason I say that is that if you write like a Python program, what you're doing is you're writing a computer program, and then you're giving it to another computer program, Python, which is written in C, and then runs on the computer. So the program that's running directly on the computer is written in C. Now, C itself is and on a Linux style system, the other important part of the story is that a C program can make system calls directly. The interface provided for system calls is a C interface. As we'll see a little bit later, there's a sort of assembly step that you have to go through to do it, but the design is explicitly to make doing it from C be the sort of native or most comfortable way to do it. Now, the hardware itself doesn't run C. The hardware runs processor instructions, CPU instructions. And actually, the way those CPU instructions are encoded as data is as sort of a binary data encoding. And we call that mechanism for encoding instructions so that it can be understood by the CPU machine code. Machine code isn't especially easy to read for humans, but it's what the hardware is designed to actually execute. So the CPU runs machine code, which is a sequence of instructions encoded in binary. Humans would prefer to not deal with things that are encoded in binary, so we have an encoding for a sequence of CPU instructions called assembly. And in assembly, the instructions are encoded as text, human readable text. So we can see one instruction, the next instruction, the next instruction. In fact, in assembly, we have one instruction on each line of text. Now, in order to be able to actually execute our assembly, we need to run it through a program called an assembler, which turns it into machine code. But most of the time, we would prefer not to write assembly code. We don't want to think one instruction at a time. We want to think at a little bit higher level. So the normal way that we're going to write a computer program is we're going to write C code, and we're going to run it through a program called a compiler, which compiles it from C to assembly. Then if we want to run it on the computer, we have to run it through an assembler, which assembles it from assembly to machine code. And sometimes we call machine code binary because it's a binary encoding of the sequence of instructions. Now, in a modern C compiler, might go straight from the C to the binary in logically one step, but from a perspective of thinking about what's happening, it's useful to think about C as always going through assembly. That's how it happened in historical C compilers. Now, for the first couple homeworks that we're going to be doing, we're going to be writing assembly code directly, so we can see what these machine instructions look like, what sort of things they are, and so we can get a sense of when we write C code later, what machine instructions does that C code get compiled to. Let me go ahead and give an example. Now, we can still use C compilers to generate assembly. We can do this step here where we go from C to assembly. So that's what I'm going to show you next, but before I show you that, if you try to complete the assembly assignments by writing C code and running it through a compiler, the TAs can tell when that's what's going on, and they're going to give you 0 points for it. So I'm going to show you how to do it, but don't do it for the homework. All right, so let's go ahead and do this. We're going to start by writing a C program. So I'm going to open a file called hello.c, and then we're going to type in a C program. All right, so that's the most basic C program. It doesn't do anything, so let's make it do something. We're going to have it print out a message with a new line. Now, in order to compile that, I can go ahead and say gcc-o hello.c. So this is invoking the GNU C compiler. We want it to read in a file called hello.c, output a file called hello. It can tell based on the names of the files that hello.c is a C source file, and the thing that it's outputting is supposed to be a completely compiled, runnable program. So I run this, it's going to complain about some stuff. We'll fix that stuff later. And then we're going to say /hello to run a program called hello in the current directory, and it's going to print out the thing. So if I look at my current directory, we can see that we have our hello.c file, and then we have our hello file, which is green because it is a file that's marked executable, which is common for binaries that we can run as programs. So that's not terribly exciting or a boring C program. Let's do something a little bit more interesting. Let's say gcc big S -o hello.s hello.c. So this is calling the GNU C compiler, which is the standard compiler that we'll be using for actually everything. We're going to use it as our compiler and our assembler all semester. And what we want to do is we want to read in hello.c. We want to output assembly, and the place where we're going to output the assembly is a file called hello.s. Bonk, same warnings. In fact, it's exactly the same warnings. GCC isn't doing its compilation step any differently here. It's just skipping the step where it does assembly automatically. Now we have a hello.s file. We'll open that up in Emacs, and we can see the full source code for the C program. There's a bunch of stuff going on here. I don't expect you to be able to immediately read assembly, especially assembly from a compiler, which is sort of a mess, without taking the next 2 weeks of this class. But there's some stuff that we can definitely see that we should recognize. So back in the C program, we had one function called main. In the assembly program, we have a label main right here. A label is a name that ends with a colon. And so this main label here and this main function here are the same thing. They're both functions in a C program. Now, the main function here ends at this closed curly brace. The main function in the assembly ends here with the statement leave, or the instruction leave, and then the instruction ret. Every function in assembly is going to work like that. It starts at main, and then it ends with, well, all of them always end with ret. Most of them, and all the ones we're going to be writing, end with leave ret. All right. Another thing that we can see here in this thing is we have a function called printf, and we're calling it. So in the assembly code, we should have a place where it says call, and then has printf. Now the only place where it says call here is right here. The thing that it's calling is not a function called printf. It looks like what it's calling is a function called puts. That's kind of weird. Let's keep looking. All right, we have a string here. And the string that we have, the string literal in the C program says hello C program, and then has a new line at the end. Over in the assembly code, we have a string up here, a string literal, that says hello C program. There's a label here, LC0, that's mentioned right before we call puts down here. So it turns out that this is the way that we pass a string to a function, is by referencing it by a label. But we can see that we have that string up here, but it's not quite the right string. This one has no new line, whereas this one over here has a new line. So that's weird too. Now, what's going on is that the C compiler does some optimizations, and in this case it's optimizing so hard that it decided that I asked for printf, but it disagrees with me. It's going to do puts instead. I'm going to tell it to stop being so silly. And what we want to do is add a -f no built-in to this command line for GCC. It's the same command line that we used to go from C to assembly before, but now we're saying no built-in. No space. F no built-in, bam, same warning. Open up that assembly, and now our assembly code is slightly different. Our string has a new line, and the function that we're calling is called printf. So now we can see that once we get rid of that little bit of optimization, the structure of this program here, there's a main function, it calls printf, it passes a string hello C program new line, and the structure here, there's a main program, it calls printf, it passes a string hello C program new line, is the same. And that's going to be true for every single C program. Every single C program can be compiled to an assembly program that does exactly the same thing. Not only does it do exactly the same thing, it is exactly the same program. Since every C program logically goes through assembly, you can always get the same result writing a C program and just manually writing exactly the assembly program that the compiler would output. So C and assembly are the same thing in a meaningful sense. All right, let me give another example. So that was hello. Let's write another C program called add1.c. So every C program is int main, int argc, char pointer, argv array, return 0. This program is going to have a second function in it, though. It's going to say long add1, long x, return x plus 1. Long x is add 1 to 5. Printf x equals long decimal. All right, so there's my program. So again, gcc add1.c, we compile it, we get the same warning about not declaring printf, we run it, and x is 6, which is what we would expect. We took 5, we called a function which adds 1, and we print out the result is 6. Let's get the assembly. gcc big S O add1.s, add1.c. So if we look in here, what we expect is that this program has two functions, an add1 function and a main function. In assembly, functions start with a label and end with ret. So we should have a label add1 ending with ret. Label add1 ending with ret. Label main ending with ret. There's the string that we expect hanging out there. And then the other thing that we expect is that over here we have an arithmetic operation where we're taking two numbers and adding them together. So we would expect there to be an add instruction somewhere in the assembly. Right here we add 1 to something. That is where the add 1 step occurs. We'll talk more about like the details of instructions later, but again, we have a correspondence between C and assembly. A function in C, a function in assembly, the same sort of thing. Now there's a couple of weird things going on. So in main, before we call add1, it says that it's going to move 5 into a register. Those are the things that we name with %signs here, called EDI. Then we call add1. Up in add1, we expect to find a reference to EDI, because that's where it put the 5. But looking through, we don't find a reference to EDI. Instead, we find this reference to RDI. And then that gets moved through this other thing over into RAX. That's where we finally add 1. So trying to understand what's going on here is a little bit weird. And I want to go ahead and take a look through some history on this AMD 64 architecture so we can try to figure out what these registers mean and what all is going on here and why down here we stick our 5 in EDI, but up here it looks like it's expecting to get it back out of RDI. So to do that, I'll come back in the next video.